In this section, we introduce increments and differentials. Increments are useful and they provide an alternative notation for defining the derivative. Differentials are often easier to compute than increments and can be used to approximate increments. Okay, so we define the derivative of f at the point x as a limit of the difference quotient. So f prime x equals limit when h goes 0 f of x plus h minus f of x over h. Okay, this is the derivative of f at the point x. We consider various interpretations of this limit, including slope, velocity, and instantaneous rate of the change, etc. Increment notation enable us to interpret the numerator and denominator of the difference quotient separately. Okay, so given for the given function y equals x cube, if you want you can denote by the f of x. If x change from 2 to 2.1, okay, x change from 2 to 2.1, then y will change from which value? For x equals 2, y is 2 to power 3, 8. For x equals 2.1, y is 2.1 cube, which is 9.261. So the change in x is called the increment in x, okay, and which is noted by delta x. So increment in x denoted by delta x, which is 0.1, 2.1 minus 2. 2.1 minus 2, which is 0.1. So increment in y denoted by dy, that is 9.2.61 minus 8, which equals 1.261. Let's discuss this increment geometrically. For the this graph, okay, symbolically I show that. So this is the point x1, this is the point x2, like the 2 and 2.1. So for this point, that is x1 comma f of x1. For this point, this is x2 comma f of x2. So the increment in y, this is the increment in y. This is increment in y. What is that value? This is f of x2. This is f of x1. So delta y equals f of x2 minus f of x1. If we say this length is delta x, this is delta x exactly. Why? Because it's increment of the in the x, delta x equals x2 minus x1. So we can write increment in y with respect to increment in x as the following form: x1 plus increment in x, which is delta x, minus f of x1. So if you observe the above formula, the derivative formula, that is limit when h going to 0, instead of the h we have delta x goes to 0, f of x plus delta x, instead of the x1 I wrote x, f of x1 over delta x. So above is the increment of the y. So this is delta y. So the limit of the quotient of the increment in y over increment by x give us the derivative at the point x. Actually, this limit is not differential. This limit is derivative. Let's emphasize. This is derivative of f at x, at the point x. Differential and derivative are very similar for the one variable function. Actually, in this course, we will never discuss the two variable functions. For two variable functions, differential and derivative are completely different concepts. Actually, again, there is some relation between them, of course, but not exactly the same. But here you will see differential and derivative are very similar. Okay. So let's talk about differential. Assume that the limit in previous limit exists. Then for small delta x, differential quotient dy over dx provide a good approximation for the f prime. Also f prime, derivative of the f, which is provides a good approximation for dy over dx. So as you see, these are approximately the same. So that means that delta y over delta x not exactly equals, but approximately same f prime x. If delta x is sufficiently small, but of course it is not this is different than 0. Okay, so here delta x is small, but delta x different than 0. Okay, so by multiplying both sides by delta x, we obtain delta y not equal, approximately equal, sorry, f prime derivative of the f times delta x. So increment in y approximately equals derivative of the f at the point x times increment in x. Okay, so from this equation we can observe that f prime times delta x provides a good approximation for delta y when delta x is small. Because of practical and the theoretical importance of the f prime delta x, we give it the special name differential and represent it with the special symbol dy or df. Actually, this is increment. This is increment. We write that one dy equals f prime x dx. Actually, dx for the one variable case exactly equals delta x. So increment in x equals differential of the x. But increment dy not equal. Okay, this is approximately equals delta y. So maybe step by step let's continue. We define the right hand side of the this approximate equation. This right hand side is defined as a delta y. Okay, so that is the differential of y. So this is that one. By definition, differential of the y is defined as the following equation. Okay, so this is the differential of the y. That is differential. But in general, we know maybe by considering the f of x equals x function, you can sense, okay, easily. Delta x equals x, okay, this is easy in my opinion for you. So for the function f of x equals x, also dy can be noted by dx. This is the equivalent df, okay. So here df or dy, does not matter, equals derivative of the f is 1 times delta x. So From here, we obtain delta x equals dy, what is y? Let's write. Here f of x is y, so y equals x. So this implies dx equals delta x, okay? So this is dx. So in general, we know the following fact. Differential of the y equals f prime x dx, differential of the x, okay? We obtain this formula.